Hello everyone. In this video, I'm going to help you to go over the mock exam which I gave you in preparation of the upcoming May exams. So let's get to the work. All right. So define acceleration. This is going to be straight to the point. Rate of This is the typical definition of acceleration, rate of change of velocity. You can give it in other words and say acceleration is change of velocity per unit time. That's also acceptable. Or you can give an equation that says velocity over time. That's acceptable as well. So choose which one is more okay with you and go with that. We are given a speed time graph for the motion of a car, and this car's motion is in 3 stages. From rest, that is time equal to 0, up to 15 seconds, the car accelerates constantly to a speed of 28 meters per second. So when time is 15, the car will be moving at 28 meters per second. So 10, 11, 12, 13, 14, 15. Okay. So that's the first stage of the journey. The second stage, from 15 seconds to 32 seconds, the car maintains a speed of 28 meters per second. So the car keeps 28 right up to that stage. Let's put this down on paper. So these are the first 2 stages of the journey. Constant acceleration is indicated by a straight line, and constant speed is again indicated by a straight line over here. The last leg of the journey is a little bit tricky, but we can manage it. From time equal to 32 seconds, the car has a constant deceleration of 2 meters per second until it comes to rest. So we don't know the time at which the car stops. We don't know that time, but we can find it. The car is traveling at an initial speed of 28 meters per second, and it's trying to go to a final speed of 0 meters per second. It's using an acceleration of 2 meters per second. I'm going to call it -2 because it's a deceleration. We need to use the formula V is equal to U plus AT. And if we rearrange the quantities, we will have T equal to V minus U divided by A. This is why it's important to know how to do subject of formula. And we are going to have V is 0 minus 28 divided by -2. That gives us a time of 14 seconds. So the car took 14 seconds to get to rest. So now we are at 32 seconds here. We add 14 seconds, 32 plus 14, which means this car stopped at 46 seconds. So we draw a straight line graph indicating that. So this is our speed time graph for this journey, and I think it's pretty doable. All right. From time 15 seconds to time 32 seconds, the path of the car is part of a circle. So we are now talking about circular motion. The resultant force is always pointed towards the center of the circle. So okay. What happens to the velocity of the car? Look here. During that leg of the journey, the car speed is not changing. But if it is traveling in a circular motion, the direction keeps changing. So velocity therefore also keeps changing. So keeps changing. What is making the velocity to keep changing is the change in direction. The speed is constant, but the change in direction. All right. So that's it for 8 marks. The second question says, diagram shows a spring balance used to measure the weight of a baby. The spring inside the balance extends when a mass is suspended from it. The dial shows the extension of the spring as a value of mass in kgs. The spring obeys Hooke's law up to a weight of 175 newtons. State Hooke's law. So Hooke's law says the extension of a spring is directly proportional to the force or the applied load if the limit of proportionality is not exceeded. So you just need to memorize that one. State the relationship between mass of the baby and the force exerted on the spring due to the baby. The relationship between mass and the force, in this case, the force is the weight of the baby. So weight is equal to mg. Weight is equal to mg. It would be a good idea to say m equal to mass of the baby and g is the acceleration of free fall or the gravitational acceleration constant. The reading on the spring balance is 8 kg. Determine the force exerted on the spring due to the baby. Again, the force is the weight. So weight is equal to mg. M is 8 and G is 9.8. And from there, we are going to get a rounded figure of 80 newtons. we get 78.4. So we can write it as 78. We don't need to write 80 here. 78, sorry. So that's going to be our solution. All right, another question. An aeroplane of mass given lands with a speed of 62 meters per second on a horizontal runway at time equal to 0. It decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6 meters per second after a time of 35 seconds. What is the deceleration of the aeroplane in the 35 seconds after it lands? So we are going to use V is equal to U plus AT again. V is the final speed of the aeroplane. In this case, it's 6 meters per second. The initial speed is the speed with which the aeroplane landed, and it's 62 meters per second. The time to decelerate, 35 seconds. So if we make A the subject of the formula, we have A equal to V minus U over T. We substitute 6 minus 62 over 35. And I'll punch in my calculator. We get a deceleration of minus 1.6 meters per second squared. Now, the word deceleration already includes the negative part. So we are going to write 1.6 meters per second squared. The word deceleration is substituting the negative sign. If the question was saying acceleration, we were going to maintain the negative sign. The resultant force acting on the aeroplane as it decelerates, we use the formula F is equal to ma. So it's really just about substituting here. M is 2.5 times 10 to the power 5, and A is this one which we calculated, 1.6, and we get our force from the calculator. We are going to get, don't forget the unit, there we go, that is 400,000 newtons. Now, when the aeroplane is traveling at a speed of 6 meters per second, what will be the momentum? Momentum is equal to mv, and m is given 2.5 times 10 to the power 5, and V is given. So we have a momentum of 1.5 times 10 to the power 6. The units of momentum are basically the units of mass multiplied by the units of V. So kg from mass and meters per second from V. That is our solution. At t equal to 35 seconds, The aeroplane stops decelerating and moves along the runway at a constant speed of 6 meters for a further 15 seconds. Sketch the shape of the graph for the distance traveled by the aeroplane along the runway between t equal to 0 and t equal to 50 seconds. All right, so this is the kind of graph one would be expected to provide. At the beginning of the deceleration, before the aeroplane it decelerates a lot, it will be moving fast. Then after some time of decelerating, the plane is now moving slow. How do we know that this is fast and that is slow? We look at the gradient of a distance time graph. The gradient of a distance time graph represents the speed of the object. So we have steep means higher gradient, therefore fast. Gentle means less gradient, therefore slow. Then we have this part. It's a straight line. That's what I tried to do. Draw a straight line. And that means speed is not going up or down. If it's a distance time graph and it's straight line, it means the speed is not going up or down. So we are maintaining the speed by drawing a non-horizontal, non-vertical straight line. There we go. So that's the expected graph right there. We have another version of Hooke's law, maybe not Hooke's law exactly, but this is the loading of the spring. The diagram shows the extension load graph for a light spring, and we can see the graph is a straight line up to here. So this point where the graph starts to bend has a name. I will ask you, what is that name? State the range of loads for which S obeys Hooke's law. Well, we have already answered this. 0.0 newtons to 8.0 newtons. Using information, determine the spring constant K of spring S. We know Hooke's law says F equal to Kx. So K is equal to F over X. And that gives F equal to 8 minus 0 over X, which is from here right up to here. So that's from 0 to 15. Uh, 15 minus 0. Okay. Okay. We get 0.53 newtons per centimeter. That's the expected solution right there. A scientist fills a container with seawater. The container is given dimensions, density of seawater is given. Calculate the mass of the seawater in the container. We know from density equal to mass over volume, we can say mass is equal to density multiplied by volume. So in this case, mass is equal to density 1020. Volume is length times width times depth. So 30. Oh, there is something we need to be careful about, and that is converting our dimensions to meters. Why are we converting to meters? Because density is given in cubic meters. So that's going to be 0.3 times 0.3 times 0.4. I'll punch in the calculator. All right, I am getting 36.72 kgs, which we can round off to 37 kgs. Now the submarine is fully submerged in the sea. The atmospheric pressure is 100 kilopascals, and the total pressure on top of the surface of the submarine is 500 kilopascals. Calculate the depth of the top surface of the submarine below the surface of the sea. I'm going to draw a small diagram here. Let's suppose this is the sea level and the submarine is here. We are going to have this pressure of 100,000 pascals due to the atmosphere. Then we are going to have an extra pressure taking us to 500 kilopascals. The extra pressure, let's call it X, is due to the water. So if we say 100,000 plus X, we get a pressure of 500,000. Like that. So X is 400,000. The pressure due to the water alone is 400,000. And this is the pressure we want to use. In our calculation, we know that when we are dealing with fluids, pressure is equal to H rho G. H is the height. In this case, it is the depth of the top of the submarine below the sea. So we make H the subject of the formula. H equal to pressure divided by rho G, giving us H equal to pressure. We use the pressure of water alone, the pressure of water alone, which is 400,000 pascals. And we divide that by rho, which is 1020. The rho is the density, and it has been given up here. G is given at the beginning of our question paper. It's 9.8. So we do the calculation there. We get 40. So the depth of this submarine is 40 meters in the sea. H, which is an opening door on top of the submarine, is an area given. What is the downward force on the H? due to the total pressure on the top surface of the submarine. We know pressure can be given as force over area. We have the pressure, we have the area, we need the force. So F is equal to pressure multiplied by area. The pressure on the H, which is a door, is 500,000 pascals. Or the pressure, which is the atmospheric pressure plus the water pressure, all that pressure is exerted on the H. Now, we can say force is 500,000 times 0.62. You punch that in your calculator and you get 310,000 newtons. All right. This question talks about a double-decker bus where we have two passenger compartments. You have the top compartment, you have the bottom compartment. These are very popular buses, especially in countries that use mass transit. So, this bus is being tested for stability. The angle the bus makes with the horizontal is gradually increased until the bus begins to fall over, which is toppling. Explain why the bus begins to topple. When it comes to stability, if the center of mass is the line of action of the weight which starts acting at the center of mass, if it comes through the inside of the bus will remain stable. But if the line of action starts acting outside the center of the bus, we are going to treat the wheel of the bus as the pivot, and now this force, which is acting outside the bus, is now creating a moment, and that moment is responsible for rotation. That is the falling over. So, when the center of mass of the bus is in a position where the line of action of that center of mass goes outside the bus starts to fall over. So, okay. So, the line of action of center of mass or center of gravity is outside the bus, causing unbalanced moments. This is what causes objects to topple over. If the center of mass is very high, the bus will quickly topple over. If the center of mass is very low, let me show you. If the center of mass is up here, it's going to quickly get out of the bus. But if the center of mass is down here, it's going to be difficult. The bus will need to really bend a lot for that center of mass to get out. So that is why a lower center of gravity is better than a higher center of gravity. So if there are 30 passengers in the upper compartment, it means the center of gravity of this bus will go up. And when the center of gravity is elevated, our bus is going to be unstable. The line of action of that center of gravity will easily move out of the bus when it is tilted. So you want the center of mass to be lower rather than elevated. In this question, we are looking at a person who is crawling on top of ice. And now the question says, explain why this way of moving across the ice is safer than walking. Use your understanding of pressure in your answer. Okay. Now, when you look at what's going on here, the person is trying to increase their cross-sectional area. And why is it necessary to increase the cross-sectional area? Because they are walking on top of a fragile medium. So this medium would break if you exert too much pressure on it. The medium being the ice on which the person is crawling. So those are the ideas you are expected to share. The first point is this person is increasing cross-sectional area so that pressure is less. All right. So the person has increased their cross-sectional area to reduce pressure, and this idea is supported by the equation pressure is equal to force over area. Force is the weight of the person and is constant. There's nothing that the person can do about their weight in this scenario. So they manage the area then. Why would they worry about managing the area? Why don't we walk every day crawling all over the place? This is to protect the ice, which is fragile and cannot withstand the pressure. There's no need for us to protect the ground which we walk on every day because it's strong enough to withstand the pressure. If the ice breaks, this person will sink into the water beneath the ice. So for the safety of this guy, they have to crawl. Fig 4.2 shows a side view of the pond with a layer of ice floating freely on the water. We are given the details. Calculate the pressure at point X due to the ice and the water. The pressure which is felt at X is the sum of pressure due to the ice plus the pressure due to the water. The pressure due to the ice, we say P is equal to force over area. And that's going to be, force is mg, it's the weight of the ice. With regard to the ice, the force is the mg, mass of the water multiplied by the gravitational field strength. So mg divided by area. Now, mass of ice is given. We are looking at 690 multiplied by 9.8. We divide this by 5. This gives us the pressure due to ice. So we punch in the calculator. This is 1352.4 pascals. How about the pressure due to the water? Let's say P water. To get the pressure due to the water, we are going to use H rho G. H is the depth of the water, which is 0.45. Rho is the density of the water, which is 1000. And J is 9.8. Punch in the calculator. Pressure due to water is 4410 pascals. All right, so our answer would be 1352.4 plus 4410. And that gives us, okay, we'll round it off to 5,800 pascals. Okay, so that is the pressure at point X. The diagram shows a boy throwing a ball at an object in a fairground. The ball has a given mass and it travels with a given speed. Let's calculate the momentum of the ball. Momentum is equal to mass times velocity. The mass, let's convert it to kgs. We will have 0.190 kgs, and the velocity will keep it 6.9 meters per second. Okay, if we punch in our calculators, we get 0.19 times 6.9. 1.311, 1.3 kg meters per second. Okay. After hitting the object, the ball bounces back along the same straight path with a speed of 1.5 meters per second. The object has a mass of 1.8 kgs. Calculate the speed of the object after it is hit by the ball. We are going to use the idea that momentum before is equal to momentum after. Before the collision, the momentum is coming from the ball only. And after the collision, we now have the ball moving in this direction, which is minus 1.5 meters per second. The negative sign is due to direction. When an object bounces backwards, if the original direction was positive, then the new direction is going to be negative. The object which was hit by the ball, let's let's assume it goes in this direction. So we have 0.19 kgs here, and we have 1.8 kgs over there. Momentum before collision was 1.3. Momentum after collision is, we take these two and we calculate their momentum. So we have minus 1.5 times 0.19 plus the momentum of the object, which is 1.8 for mass, and V, which we don't know yet. That's going to give us this linear equation, which I'm just going to quickly solve. Okay, once we solve the linear equation, which is this linear equation, we end up with speed being 0.88 meters per second. Let me just give you a quick warning. You are most likely going to remember this equation. The challenge may be on remembering the negative sign. And the reason why we are including the negative sign is, originally the ball was going in this, let's assume it was going in this direction. And this direction was considered positive. How do we know it was considered positive? We were given this positive number. When it hit the object, it bounces back, which means the ball is now bouncing backwards. This new direction should be considered negative. And this is the reason why we brought this negative on 1.5. It is their typical trick. So try to make sure you understand it. If you are not understanding it, questions are welcome. This question shows a golfer about to hit a golf ball with a golf club. The initial momentum of the golf ball is 0. It's not moving, so it's 0. Define momentum. So momentum is the product of mass and velocity of an object. So you can just say mass times velocity. That's acceptable. The golf ball is in contact with the ball for that time, and the velocity of the golf ball as it leaves the golf club is given. The golf ball has a mass given. Calculate the impulse of the golf ball. Impulse, in this case, is going to be referred to as change in momentum. So momentum before we hit the golf ball, let's say P before is 0, P after equal to 41 times 0.046. This is the momentum after. So what is the equation of impulse? Momentum after minus momentum before. We are going to say 41 times 0.046 minus 0. And let's see what we get. We get 1.886 Newton seconds. 1.8, oh, let's just round it off to 1.9. 1.9 Newton seconds or kg meters per second, whichever you choose. Calculate the force applied to the ball by the golf club. Again, impulse is equal to change in momentum. F is equal to, and change in momentum is this one, 1.9, and T is this time given here. That gives us, I'll put the rounded off value of 3,800 newtons. So that's our force. The diagram shows a barrier at the entrance to a car park. The wooden barrier arm has a weight of 60 newtons, which acts through the center of gravity at the position shown on the diagram. Okay. Initially, the wooden barrier arm is horizontal. Use fig 7.1 to calculate the clockwise moment of the weight of the wooden arm about the pivot. The clockwise moment is due to this force alone. That is the only force responsible for clockwise moments. So we are going to use the formula moment equal to force times distance. It has to be a perpendicular distance, and from our diagram, everything is set up well. That gives us 60 multiplied by 1.7. All right. Our answer is 102 Newton meters. The wooden arm is in equilibrium. The mass of the soft iron bar A is 32 kg. Calculate the distance D between the pivot and the joint holding the soft iron bar A. So the distance D, to calculate D, we need to figure out the weight of this soft iron bar. We are going to use weight equal to mg. The weight is the downward force due to the soft iron bar right there. So mg, m is 23 and j is 9.8. That gives us 225.4 newtons. All right. So we will use clockwise moments equal to anti-clockwise. The clockwise moments we found there are 102. The anti-clockwise moments, we are going to say this force multiplied by this perpendicular distance. and we will find D equal to 102 divided by 225.4. All right, that is the distance we get. That is the distance we get, 0.045 meters. A 50 centimeter rule is balanced at its midpoint. A force of 8 newtons acts at a distance of 10 centimeters from one end of the rule. Calculate the moment of the 8 Newton force about the pivot and give the unit. Okay, moment is equal to force times distance from the pivot. Now, this is a 50 centimeter rule, which means from pivot to the other end is 25 and to the other end is 25 centimeters. If you say 25 minus 10, you will find this distance here. That's 50 centimeters, which is 0.15 meters. So moment is going to be 8 multiplied by 0.15 Newton meters. And that gives us 8 times 0.15. Okay. 1.2 Newton meters. That's going to be our solution. Another force acts at a point 10 centimeters from the pivot. It makes the rule to balance. Draw an arrow to show the position and direction of this force. This is giving us anti-clockwise moments. We need another force that gives us clockwise moments. So we are going to have a force here, 10 centimeters, and this is our force. It's giving us clockwise moment. It will also be correct to put that force here, pointing upwards. So 10 centimeters pointing upwards. This will give us clockwise. So the idea is to provide a force that gives clockwise, because for equilibrium to happen, equilibrium is balancing, which is referred to here. We need to counter the given anti-clockwise force with our own clockwise force. All right. Fig 3.2 shows a bicycle fitted with wide tires and a bicycle fitted with narrow tires. Use your ideas about pressure to explain why wide tires would be used over soft ground. I'll leave this question for you to attempt using ideas similar to what we said when we were discussing that person who was crawling over ice. The diagram shows a computer on the surface of a desk. The weight of the computer is given. The area of the computer in contact with the surface of the desk is given. What you are going to do here is, first of all, take note of the units. We are not going to convert to SI units. We'll keep our unit of pressure in non-SI units. So pressure equal to force over area. Force is 48. The area is 20. So 48 divided by 20, we get 2.4. A student uses a force of 12 newtons to tilt the computer as shown in Fig. Okay. Calculate the moment of the 12 Newton force. We are going to use moment equal to force times perpendicular distance from the pivot. So this is the distance which we are going to be interested in, and that's 32 centimeters. So 12 times 32. Our unit is in Newton centimeters, so we don't need to do any conversion. 12 times 32. That's our answer. Okay, guys, enjoy the remaining part of your holiday and practice. Bye-bye.